Good morning, good afternoon, greetings, everybody. So let me showcase the today's agenda before we start this webinar. Okay, so this is how the agenda is going to look like for today's webinar. Introduction from the individual presenter, and then we are going to take 5-10 minutes to talk about company overview. Since many of you joining this webinar might not be familiar about DEP company background and all, but we are a well-known company in the Detroit region. We are working with most of the OEMs and tier one supplier. But we thought probably before we deep dive into the BTR Sensor, we could take 5-10 minutes and talk more about company background. And then our colleague Yusuf will take a deep dive into the BTR sensor demo, which would last for like 30-35 minutes. And then we would have a dedicated Q&A a slot allotted, probably for like 10 minutes or so. Okay. And when it comes to the Q&A, the way we have designed this entire webinar, any participants adding questions in the chat and all, it will be only visible to DEP people. Okay, it will not be publicly available, for all the webinar attendees. So all your questions will be private and only visible to DEP. Okay, so while we are presenting the media sensor demo and all, if in case you have any live questions, feel free to drop your questions in the chat window, and once we go to our Q&A session, we would pick your questions, and we'll address it during the Q&A slot. And once that is done, we are going to just wrap up this webinar by highlighting how exactly the next step are going to follow, how post this webinar, how further we can address your questions, and based on your further interest, how further how I mean dedicated discussions can be scheduled and all. Okay, so those things we are going to cover. So with that note, let me jump into the company presentation. So DEP stands for Detroit Engineered Products. We are a 27-year-old company now. We started in the year 1998, and we are headquartered in Troy, Michigan. So overall, we have presence in 13 plus countries, working with almost like 300 plus customers, all the way from OEM and tier one companies. So and we have offices, global offices in India, China, Japan, Canada, Mexico, South Korea, and in Europe, we work with our partners. Okay, I mean France, Italy, Germany, Poland, Turkey, Spain. So right hand side, what you see, these are all the five business vertical we are operating today as we speak. First is engineering consulting. Here we do all type of turnkey projects, ODC engagements for design and engineering, whether it is mechanical, electrical, electronics, mechatronics, anything on the design side, CAE virtual validation side, CFD controls, systems engineering, all that comes under engineering consulting division. Sorry. Then we have product development. Here we support end-to-end product development activities. Then we have talent acquisition, where we provide people on contract for short-term and long-term engagements in North America, Canada, Mexico, and as well as in globally as well. And then DEP Meshworks. So this is our own proprietary software. It is both pre and post processor. We sell this. We also sell this software to our customer. And then DEP AI works. So we have developed our own machine learning AI platform. Okay, so these are all the five verticals we are operating as we speak today, and I'm going to cover all these five verticals one by one in my upcoming slides. I'll try to keep it very confined. Probably I'll aim to finish it in next 5-7 minutes, and then we can jump into the BTR technical demo. So when it comes to the engineering consulting, we can proudly say that we could be our one-stop service provider for all your product needs, all the way from design and engineering, starting from the benchmarking, where we can tear down your products, your competitive products. We have our own lab at Troy office. We can scan all the components and convert the scan data into CAD models, FE models, and we can do the further benchmarking studies. I mean the CAE quality studies, for performance validation, those type of things, we can support it. And design, we support companies for anything, product detail design, mechanical component, electrical component, all the way from 3D modeling, 2D drawings, layout drawings, schematic drawings, we can support it. And CACFD, we are very strong. When we started this company, we started as a software company. Okay, so by default, you can take it for granted. Any type of CA virtual validation, whether it is on the powertrain side, vehicle engineering side, we can support that. Okay, on the performance simulations, multi-material optimization, lightweighting, thermal management. Okay, I mean we can support it. And on the control side, we do all hardware and software controls, the entire V cycle we support. On the manufacturing side, we support companies for mold flow simulations, formal simulations. We can do that, and prototyping. This we do it in India with our partner companies, sister companies. We have the systems available, and electrification and mobility. We are working with most of the EV companies in North America and globally as well. Okay, so we are doing a lot of work in the electric powertrain domain, all the way from EDM, EDUs, battery motors, power electronics. Sometime on the component level, sometime on the subsystem level, or sometime for the entire vehicle development. Okay, and then AI/ML. Okay, so this is I already spoke about. Okay, we had developed our own machine learning platform. So as you can see, this entire product development life cycle, we can support. Okay. So this is just an extended list of the consulting services what we are offering. So bumper to bumper, commodity by commodity, how we are supporting our customer. Okay, we need to admit that. Okay, our 85 to 90% of business is coming from the automotive, and working with more than 300 plus customers. Okay, so this is a pretty comprehensive list. Okay, you can say a skill metrics, from our end, how we are supporting, into various commodity. Okay, so the left hand side, you can see these are all the functional areas, and the top right, top row, full vehicle, BIW, subframe, bumper, suspension, exterior, interior, seat, battery pack. Okay, this is a pretty comprehensive chart, how we are supporting our customers. So coming to our product development, this is where we have developed, some innovative products. Again, since we are a service industry, we are not mass producing any of this product. The idea behind to develop all this product, okay, because we would like to showcase it to our customers, like, if DEP has the capability to support the entire end-to-end product development cycle. Okay, so these are all our in-house projects that we had done in collaboration with customers. Okay, some of them. So this is the electric two-wheeler scooter that we have developed for the India market. This is the electric farm cutter. This is the single-cylinder engine that we have developed in collaboration with Aramco. This is the combustion sensor. This is the drone. Okay, so this pretty much gives a good snapshot, like when it comes to the product development. How we can support it. Now coming to the talent acquisition, any short-term requirement you may have, or long-term requirement you have, on-site in US, Canada, Mexico. Okay, we can support that. We are already an approved vendor. Okay, for a couple of OEMs. We have vendorship, from a couple of defense companies in US. Okay, and we support them in multiple domains. Whether it is ITAR requirement, non-ITAR requirement, automotive requirements, all the way from design, CAE, CFD controls. We support any type of contract labor requirement you might have in the US. You can also count DEP for that. Now coming to our software division, DEP Meshworks. So like I informed in my previous slide, this is our own proprietary software. It is both the pre and post. It is both the pre and post processor. Okay, and we also sell this software to our customer. Okay, but one thing to note, okay, whenever we do any consulting projects, okay, whenever we do any services project, we use this technology as a value addition apart from our overall engineering knowledge. Okay, so this is one of the differentiator, okay, that separates DEP from the other competitors. How we are doing our day-to-day engineering. Okay, Okay, so whether it is meshing, morphing, parameterization, topology optimization, okay, I mean this meshwork software has got a lot of magic and advanced features as compared to the competitors' software available in the market. And coming to the next DEP AI works, this is getting very popular in the market. Okay, so DEP had developed our own machine learning platform. Okay, I mean we are doing a lot of AI prediction. So as long as you have data available from your previous designs, we can bring that data and we can feed that data into this AI platform. Okay, and we can predict the performance without going through the normal simulation. Okay, and the beauty what and the advantage, okay, what we add here, I mean since we are coming from the engineering background, okay, we know that, okay, I mean what problem based on the problem definition, what data size it might require, I mean how we have to train the model and all. Okay, so that comes with the experience. Okay, so that is one advantage. And based on, and since we have the meshworks parameterization technology available, even a lot of customer may not have the data available. Okay, so with our parameterization technology, we can create a lot of synthetic data, sample data, with this technology, and we can feed that data into this machine learning platform. Okay, so if this something impressed you, then probably we can have a separate session and we can talk more about this AI/ML technology, how it works. Now coming to our global strength, so globally we are 850 employees. In US we have 100 plus employees, and majority of the strength that we have in India. Okay, so in India we have four locations: Chennai, Bangalore, Pune, Tirunelveli. Okay, the reason we expanded a lot in India because the way we are engaged with our customer, it's a hybrid model. Okay, we keep 20-30% in US and rest of the heavy lifting we do it from India. Okay, so that really brings confidence with the customer, that they are getting local coordination in US, and most of the heavy lifting, where they can also get leverage of cost benefit and all, like, from the low cost center. Okay, so that is how we are structured with most of the arrangements what we have with OEMs tier one and globally as well. Okay. So whatever you see on the map, the red phones, these are all our offices, and the blue phones, here we are working with our partners like Germany, Italy, Poland, France. We work with our partners, and industry-wise, we support a wide range of verticals. Okay, but our primary focus is on automotive. But we do have some customers coming from aerospace, consumer electronics, biomedical engineering, and so on. Now coming to our customer base, I mean we have more than 300 plus customers. Okay, so probably I mean this is just a very partial list. Again, not possible to put all the customer name in one particular slide. So in North America, you can see we have all the major OEMs: GM, Stellantis, Ford, Honda, Nissan. So geography wise, again, I mean these are all known OEMs and tier one suppliers. Again, some are OEMs, some are tier one. Some we also have quite a few EV makers. So we have multiple engagements with them. Okay, sometimes we support them on consulting projects. Sometimes we support, sometimes we sell our software, or sometimes we support them, with the contract labor requirement. Okay, so I think this would be my last slide. Okay, so in terms of ISO certification, now okay, we are all covered. Okay, so you can have full peace of mind that whatever work we are going to deliver, it is going to meet all your quality standards. We have all ISO 9001 certification and all, and we are also a women-owned company. Okay, we are also a minority business enterprise. So sometimes companies do get some subsidy benefits, working with company like us. Okay, so I think that should be all as a company overview. If in case anybody has got any questions, whatever the slides I just showcased, feel free to drop your questions in the chat, and probably we can pick it up during our Q&A. With that note, I'm going to hand it over to our next presenter, Yusuf, to start with our BTR Sensor demo. Thank you.
Hi everyone. Hope you guys can all see my screen now. Okay, so welcome to the webinar. My name is Yusuf Mansour. I'm a mechanical engineer, but I've been working at DEP for the last 7 years. A good portion of it on this project here, thermal runaway sensing. So we'll go through 2 topics today. So there's understanding thermal runaway, and then we're going to introduce our technology. So starting with understanding thermal runaway. Thermal runaway is the propagating exothermic reaction that a battery undergoes, leading to a dangerous situation if not mitigated properly. So I have here a list of triggers to thermal runaway. There's temperature increase, physical damage, overcharging, manufacturing flaw, and excessive usage and aging. So these all lead eventually to an internal short circuit. So for example, an increase in temperature can be due to atmospheric conditions, or it can result from other triggers. This increase melts the separator between the anode and the cathode, creating that internal short circuit. Now, physical damage can be due to punctures or deformations, typically from vehicle crashes. This can result in the battery short circuiting internally and externally. Overcharging and excessive usage can heat the battery, resulting in an internal short circuit, the same way that an internal increase trigger does. Aging can degrade the battery to the point where its the chemicals inside can end up short circuiting the battery, similar where it heats up the separator, just like in the temperature increase. There's manufacturing flaws, a rare but possible scenario where it can cause an internal short circuit in the battery even during normal operations. These can be due to many things. They can be resulting from debris or even impurities in the battery. Now, all of these short circuits ramp up the temperature and propagate to other cells, causing this thermal runaway. So, thermal runaway can lead to safety issues. Failure to safely mitigate the thermal runaway can result in the battery producing toxic gas and other harmful chemicals into the atmosphere. Now, any bystanders or passengers in the vicinity can inhale these hazardous gases, causing harm to the individual. These same toxic gases are flammable, and the heat generated from the thermal runaway can cause the battery's electrolyte to combust or explode, resulting in fire and debris to project outward. So this all makes it unsafe for bystanders and passengers. Now, the pressure buildup and the combustion from the thermal runaway can cause structural damage to the battery housing and the vehicle itself. This results in more wasteful material, and it renders it difficult to recycle. So to ensure battery safety is properly maintained, we have three key components. There's correct adherence to the battery regulations, early detection of thermal runaway, and continuous monitoring with the BMS set to take proper protocols once thermal runaway is detected. To detect the thermal runaway, sensors are necessary. There are sensors already out in market like gas sensors, thermocouples, voltage monitoring, and pressure sensors, all of which are placed outside the cell. So all of these can delay the detection because they're placed outside the cell, so it's not exactly ideal. So gas sensors detect after the venting of the gases. Thermocouples react slowly to internal thermal changes. Voltage monitoring fluctuates during normal use. And pressure sensors have a low signal to noise ratio. So to accommodate for the downsides of these sensors, there are combination thermal runaway sensors that are built with some or all of these to reduce their variability. These result in complex calibration matrices across all the detection types and can result in false positives and negatives. Our sensor, on the other hand, is not like these other ones. It's not placed outside the cell, it's placed inside the cell. And it detects the electrochemical changes before any of the vapor leakage or even the relief seal breaking on the prismatic cell. So this gives us the earliest detection of thermal runaway because it's not dependent on any gas venting or any thermal lag. And due to this, it also gives us a high accuracy with no false positives or negatives. So in the stages of thermal runaway, there are key steps like, for example, the first stage, the metal ion dissolution, where heat breaks into the crystal structure of the cathode, resulting in the migration of metal ions into the electrolyte. The next stage, in the solid electrolyte film, interface film decomposition. This releases more heat and resulting in more ion dissolution. After that, you have the reaction between the lithium and the electrolyte, which releases more heat and causes a chain reaction of degradation processes. The next stage after that, the separator starts melting. Resulting from that is micro internal short circuits, again, resulting in more temperature increase. Then the gas begins to vent. And due to this increase in the pressure from the gas formation, then you have the separator completely melting at the next point, causing a large-scale internal short circuit. Then the short circuit leads to the decomposition of the cathode and the electrolytes. The decomposition of the cathode results in release of oxygen, which reacts with electrolyte and can result in combustion. Decomposition of the electrolytes begins after this and releases more gas. Then you have the anode reacting with the binder material to increase the temperature more, and then the last stage is where the combustion happens from the ignition of the gases. So every point before the safety venting, it is possible to mitigate and even prevent the thermal runaway. After safety venting, it becomes much more difficult to mitigate, let alone prevent. It becomes a very difficult and almost impossible scenario. So our sensor actually detects within these first three stages, more so the second two, where we get a very early detection of the thermal runaway, much earlier than existing sensors now, where they detect at the safety venting, where all the gases end up escaping the prismatic cell and reach the gas sensors or the pressure buildup. Temperature detection can also be late. So knowing this is important. Now, due to this, we also have regulations that occur from the thermal runaway. So we have current regulations in China where it says the batteries must survive 2 hours without any fire or explosion after thermal runaway, or 5 minutes before with temperatures less than or equal to 60 degrees Celsius. Then you also have the 5-minute alert system, which pretty much there has to be some alarms that occur before any of the toxic fumes occur or enter the cabin where the passengers are. Europe has the same regulations. You have the batteries have to survive 2 hours without any fire explosion, and there's the 5-minute warning where it has to occur before any smoke or fire enters the passenger compartment. United States is a little less than that. It's a 3-minute thermal runaway event warning, where the signal and the visual sensor, so pretty much the alert, has to be active for at least 5 minutes. And the regulation about harmful gases or explosion during the thermal runaway, normal operation, anything like that, ends up coming in or going to be applicable in next year in 2027. So last here, before we start going into our sensor, we're going to go a touch base on the chemistry of what happens when the thermal runaway breaks down. So starting with a healthy cell, you have during the formation of the electrolyte starts reacting with graphite and builds a protective layer called the SEI. This then breaks off a little ethylene, tiny amounts of hydrogen and carbon monoxide, and then it settles down. Under fast charging or in the cold, lithium can plate onto the anode and grow dendrites. And the plated lithium reacts with the solvent and makes more hydrogen and like hydrocarbons. As the cell heats or ages, parts of the electrolyte, parts of the SEI and solvent break down, adding carbon dioxide and carbon monoxide and more ethylene. Then if dendrites pierce the separator, you get an internal short, Joule heating spikes and gas generation jumps. The safety vent opens and the hot electrolyte vapor is expelled. Meanwhile, cathode starts releasing oxygen, which chemically burns the solvent and pushes the system towards that thermal runaway. So that pretty much concludes our first topic. So now we're going to go into our sensor, which detects the electrochemical changes mentioned in that previous slide. So our sensor size and shape can be changed due to customer requirements. It can be as small as a dime, as you can see on the top right, with an external signal conditioning unit, or it can be all wrapped up in a package smaller than a credit card. So this sensor can be placed at the vents, in the ducts, within the modules, or even at the cell level where it can get access to the inside of the cell. So this sensor detects the electrochemical changes happening inside the battery. Now here in the vent sensor, you have vent holes for the detection. You have the sensing and conditioning circuit, which is located in the casing of the sensor, with a connector for the power into the sensor and the signal out to the battery management system. You have the mounting fins, and design of this sensor was specific to the testing rig and mounting jig that we've been using for our wind testing, but this can obviously be changed. Now for the cell sensor, the implementation of it requires a hole on the prismatic cell where the sensor will get welded to, so it can get direct access to the internal chemistry of the cell. Now this will then obviously be completely sealed, so there's no gases coming out before the seal breakage of the prismatic cell. Yeah, and in using this kind of method of detection, our sensor can also visualize flame ignition points and monitor thermal propagation within the pack as a function of time and location. And this can be used for prototype testing. So our product, what we're selling, is the sensor plus the conditioning unit. Then an external power line will be connected to the conditioning unit, and it will then communicate to the BMS or the CSC with either CAN messages or some digital or analog trigger signal. So we've done testing on our sensor, and in this testing, we've done overcharging and heating, and several other tests like cycling and so on and so forth. Now, in this test I'm showing here, we've taken a 50 amp hour NMC battery, and we placed the sensor, attached it to the cover plate and welded it with access to what's happening inside the cell. So there was a hole right underneath that sensor through the cover plate. We took this battery and we overcharged it at 1C. Now you can see here, we have a temperature graph here with thermocouples plotting here. And the thermocouples we placed on the positive electrode, the negative electrode, the relief seal, and the front wall. And here we have the red line is the battery voltage, and this green line is our sensor signal. Now, in about 14 minutes from the start of the test, our sensor sent a detection trigger signal saying that thermal runaway is processing, or it's detecting some degradation inside the cell. 9 minutes after its detection, the safety vents of the prismatic cell came off, and 3 minutes after that, the thermal runaway occurred. So we were able to detect a full 12 minutes before that thermal runaway. Now we have another heating test here, where we use the same battery, attach the sensor the same way, but instead we had a heater connected to the cell, and this heater was set to about 300 watts. So we had thermocouples placed around the same points, the positive, the negative, the relief seal, the front wall, and we also had a thermocouple placed on the heater itself. So you can see here that because this was heating, voltage of the battery did not change. But within 8 minutes, we are still able to detect that there were electrochemical changes happening inside the cell. 6 minutes after that, the cell went into thermal runaway. Now, in this case, there was no voltage, but the temperature did fluctuate in this range where the detection happened, somewhere between 60 to 80 degrees Celsius. In the previous test, however, even though the voltage ran up to where it could hit maximum, the temperature did not go anywhere above 30 degrees. So independent of the temperature and voltage, our sensor is able to detect that thermal runaway. And this test was a little bit more interesting. We had about 4 cells placed side by side, They were all 25 amp hour LMO batteries, and we had sensors placed on cells 1, 2, and 3. In the same way, we had a 300-watt heater attached to cell 1. You can see this red section here. And we ran this test to see the heat dissipation just from heating one cell. So in this test, we had a thermocouple placed on the heater for cell 1 and thermocouples placed on cells 2 and cells 3. This gray cell here did not have a sensor, but it was a 25 amp hour LMO battery just the same. So we ran this test 7 minutes in from heating the battery around 70 degrees. Our sensor was detecting some electrochemical changes. 7 minutes after that, the cell went into thermal runaway. Now in cell 2, it wasn't getting directly heated from the heater, but it was getting increasing in temperature just the same. And it took about 11 minutes for this one to increase in temperature and start degrading from inside the cell. So it reached here around 73 degrees before the cell started degrading inside, and our sensor was detecting those changes happening with the chemistry inside the cell. And 3 minutes after that, the cell also went into thermal runaway. It probably pushed from the fire that propagated from cell number 1 after it went into thermal runaway. Immediately, cell number 2 from that fire got pushed into thermal runaway. After that, we had this gray cell here also immediately caught fire. And from the fire of these 3, you'll see that cell 3, even though it had no increase in temperature, no degradation being shown throughout this process, but because just like the domino effect, the fire ended up pushing cell number 3 immediately into thermal runaway, where also our sensor detected that degradation. Now, in this next test here, which is a lot more interesting, what we did was a overcharge, but not a simple overcharge. We actually repeated the overcharge, stopped and continued it several times over. So we have, in this case, we used a 25 amp hour NMC battery, and we pushed it into overcharge at half C. So you can see this is the red line here is the battery voltage. This green line here is our sensor signal. And down here, we have the thermocouples that we placed on the positive, the negative, and the side wall. So 40 minutes into this test, voltage was increasing. Temperature actually reached around 75 degrees. Our signal maxed out in its detection. And the moment we got that maxed out signal, we manually stopped overcharging. We waited 20 minutes for our sensor to drop down to its baseline voltage. Meanwhile, the voltage, once we stopped overcharging, the voltage started decreasing. The thermocouple increased a bit, but ended up settling down and started dropping as the heat dissipated. And once our sensor settled down, we started the overcharge once more. In this case, 10 minutes passed, and our sensor detected an immediate jump in electrochemical changes. And so from that immediate jump, the moment we got that detection, we manually stopped overcharging. The voltage immediately stopped. The thermocouples detected around 102 degrees, and after stopping, the heat started dissipating and temperature started slowly dropping. So in this time, even though the voltage detected no changes, the thermocouple detected no changes, but the battery was already degraded enough that it was almost as if it's at its end of life aging. Our sensor was actually still detecting more changes happening inside the cell. It went up and down several times over, it kept detecting. You'll notice that when it settled down to its lowest point, it never settled to its baseline voltage, meaning that even at its lowest detection, there was still detection of some changes happening inside. And even when the voltage was at its lowest point here, even before we started the charging, the overcharge test, and the thermocouples reached around 43 degrees, our sensor detected a huge jump in the electrochemical changes and pretty much telling us that thermal runaway is imminent. This is going to happen. We waited about 7 minutes, and the temperature still decreasing, voltage still showing no signs of any detection of thermal runaway. The relief valve didn't release any gases, but we were able to degrade it enough that our sensor was giving us detection. So we started overcharging once more, and the moment we hit that button, the battery exploded and it went into thermal runaway. So even after several abuses of this cell, right, our sensor was still able to reliably detect any and all changes happening inside before any gas is expelled from the cell, before anything else, even when the voltage when the voltage and the thermocouples didn't detect anything, we were still able to get that detection. Now, in this last test, we actually had a 200 amp hour NMC battery, and instead of doing a voltage repeat or pushing this into thermal runaway, we decided to prevent it. So we took our chance. We took overcharged the cell at 1C. 16 minutes into the cell, you'll see the voltage was increasing, and it suddenly stopped right when we got a sensor sent out a detection signal. So this digital signal is what our sensor detected. Once we received the signal, we stopped the overcharging. So we waited about 14 minutes, waited for something to happen, and since nothing was happening, this was basically idle time. There was no reactions. We decided to start discharging the cell. And so from our detection, we were able to slowly discharge the cell to a safe voltage of 2.8 volts. Not only were we able to detect any changes happening inside before any safety venting, we were also able to have about 60 to 75 minutes of countermeasure time and decrease the voltage of the battery to a slow, safe voltage and prevent the thermal runaway from happening entirely. So outside from battery storage systems, our sensor can also be used as test equipment. So you can use this sensor for screening of battery materials. You can use it for extreme condition testing, standard of use, as you've seen, as I've just shown. You can use it to verify and validate materials, cell, and battery system design. It can be integrated with the BMS and the CSC systems. And you can actually integrate it into an alert for a test equipment shutdown. So main things to take away from this sensor. So because this doesn't work like the traditional sensors already in existence, it's not focused on any type of one gas. It's actually focused on the chemical changes happening inside the cell, its main base point. And so because of this, it's completely chemistry agnostic. It detects earlier than any of these other sensors already in existence, thermocouples, pressure, gas sensors. It provides a true early warning by detecting those electrochemical changes leading to that deterioration of the battery. It can be changed in shape and size to be integrated into your cell, module, or pack level to fit your needs. And it can be also integrated within the battery test systems as an alert for any unplanned conditions. Now, working with you, we can actually get all the requirements for our sensor so that we can start the designing of the sensor to the manufacturing and testing. So if there is a specific size or shape requirement or a specific circuit connection requirements necessary, we can work with you to get all these requirements and manufacture an entire set of sensors specific to these requirements and get this ready for testing. This can all be done within 16 weeks.
So yeah, this is our contact us. Again, our email address is provided. So please feel free to let us know if you have any questions. We'll be happy to talk to you offline, depending upon your interest.